In this screencast, we are going to look at an example of how to analyze an IR, and then we're going to look at common stretching frequencies for different types of functional groups. So let's go ahead and look at this example, and it's asking which compound, A, B, or C, gives rise to this IR spectrum. So basically what we're doing is we're going to look at the spectra and match it to either A, B, or C. Now, you need to concentrate on the functional group region above 1500. And then and with this, right, because this is where we're going to see our functional groups. And when we look here, here, and here, the big differences are our functional groups. So for example, this molecule just has a double bond. This molecule has a carbonyl and a double bond. This molecule has a double bond and an alcohol group. And so we can use those different functional groups to help us figure out what type of molecule this is. So when we look at this, there's a few things that we're going to keep in mind, okay? Carbon-carbon double bond absorbs at approximately 1650, okay? And then that carbonyl absorbs at between 1650 to 1800, right? And then those are the only ones that we're interested in. So let's look at the example here, and let's kind of see what we are. So here is 1500, here is 1600. And so we go up here, and then here is 1700. So in between here is right around 1650, and we go up and we see, look, that's probably right there is our carbon-carbon double bond, okay? So that's at approximately 1650. That doesn't come as a surprise. All three of these molecules have carbon-carbon double bonds. Now, when we look at this, we have a C double bond O. It absorbs between 1650 and 1800. We would expect that to be a peak kind of in here, and we don't see that, right? So we don't see a carbonyl stretch, and so we can rule out B. And so now we're trying to decide between A and C. The next thing you're going to do is you're going to come over here to the region above 300, and you're going to look for that OH stretch. That OH stretch is going to be a really long stretch here, and we don't see that. So then we can rule out C. So by eliminating B and C, no carbonyl stretch at 1850, no alcohol stretch here at 3500, then we can say, hey, look, this molecule matches this spectra. So the big take-home message for IR is that you are going to look and find functional groups. That's the big take-home message. So what we're going to do through the rest of this is look at the different stretching that you will see for functional groups. So we're going to look at this slide, and it's got 4 spectra. And the reason it has 4 spectra is because I want you to be able to compare different types of hydrocarbons. And we could have done it over 4 slides, but I just felt like it makes it harder to compare. So I want us to look at alkanes first. This is specific for cyclohexane. And I wanted you to see, right, that alkanes are only going to have carbon-carbon single bonds and sp3 hybridized carbons. And so if you have an alkane, you're only going to have one major absorption right here between 3000 and 2850. And that's it. That's all you're going to see with hexane. Then if we add a double bond, what you're going to see is a carbon-carbon double bond right here around 1650, like we saw on the previous example. And then you're going to come over here and you're going to see the carbon sp3 hydrogen, but you're also going to see the carbon sp2 hydrogen stretch because of the double bond shown right here. And so I want you to look and see how it's different between the carbon sp3 hydrogen with the carbon sp2 hydrogen showing and just that carbon sp3 hydrogen. So look and compare and see how that's different. Then look at hex 1-ine, and so this has a triple bond in it. And again, I want you to see there's no carbon-carbon double bond. That's gone. We've got a carbon-carbon triple bond shown here right around 2250, right? Kind of right in here. And then we have that carbon sp3 hydrogen, but now we've got the carbon sp hydrogen, and that's right around 3300. So notice that that's farther towards the left than what you see here. So look and compare and see these differences. One of the things that I love about IR is that an IR can tell me what I have, but it can also tell me what I don't have, right? So if I were to come over here and not know what this compound was, I could look here and say, well, it probably doesn't have a triple bond because there's not a carbon sp hydrogen bond, right? When we come over here and look at aromatic compounds, for example, compounds with benzene rings, what we're going to see is really kind of a mess, right? So you're going to see these peaks here, and it's this combination of carbon sp2 here and carbon sp3 here, and there's a lot of overlap in here. And so you're going to see that, but then also what you're going to see is a stretch at 1500 centimeters -1 or wave numbers and 1600 wave numbers. And that indicates that there's benzene here. So again, I want you to compare this, right, to what you see here, here, and here, okay? And so that it can help you differentiate what you see when you just have a hydrocarbon. Now, I think, just personally, that the other functional groups are easier to see. For example, this big broad stretch tells you it's an alcohol every single time. And it's really beautiful. It's very easy to notice. Alcohols tend to be my favorite molecules to look at in an IR spectra because it is so easy to see. Let's go here and look at ethers. I want you to remember ether has an oxygen in the center with 2 R groups on either side, and it doesn't have an OH or a carbonyl, so its only absorption above 1500 occurs right around the 3000 wave numbers because of those sp3 hybridized carbon hydrogens, right? So this can be a little tricky. Sometimes ethers can be a little tricky to distinguish from hydrocarbons unless you get down into the fingerprint region. Let's look at aldehydes. Now, aldehydes are really lovely, and I have to apologize. I do not know why this is pixelated. In your textbook, it's also pixelated because I was going to go and grab a screenshot and see if I could help with that resolution, but it is pixelated there too, which is really wild. So, but beyond the pixelation, let's talk about propanal, which is here. This is an aldehyde. And what you're going to see is there is a carbonyl stretch right around 1700 for the aldehyde, okay? And then you're going to see a mixture of sp2 carbon-hydrogen bonds, right? And then the sp3 carbon-hydrogen bonds. And so we can see those stretching frequencies there right around, between 2700 and 2800, okay? Now, ketones also have that C double bond O stretch at 1700. And the peak here is mostly due to the carbon hydrogen sp3 hybridized. If you look back to the previous one, what you're going to notice here is ketones, as long as they don't have any other functional groups, aren't going to have the sp2 carbon hydrogen bond, because this sp2 carbon doesn't have a bond to hydrogen, because it's not at the end of the molecule. And so that's something that you'll see when we talk about those spectra, as long as there's no other sp2 functional group, right? So you have to watch that. Let's talk about carboxylic acids. Carboxylic acids are also going to have a really broad, distinctive peak. It kind of comes down like the alcohol peak does, but you're going to have these little pointy CH bonds peeking out there. And so you don't always have those, but in most of your carboxylic acids you will. And so that is an indication that you have an alcohol from a carboxylic acid. You're also going to have this stretch here right around 1700. That's that carbonyl stretch. So those two things a lot of times indicate that there are carboxylic acids. Now, I want to remind you, IR is not the end-all be-all. We also use mass spectrometry to get information about our compounds, as well as NMR. So one method isn't perfect, and so that's why I'm using a lot of generalities here. A lot of times you'll use more than one method to classify a compound. All right, let's look at esters. So we see here's the ester functional group. Again, carbonyl here right around 1700, 1745 to 1735. And then these are carbon hydrogen bonds again. So most organic molecules are going to have a stretch right here. Now, let's look at amides and amines. Both of these have NH2s. The big difference here is that we have a carbonyl, and that carbonyl is going to show up in the 1700, 1600 region, okay? Now, we need to look at these NH stretching peaks. They're here between 3400 and 3200. And we also see these here in just the amines. The biggest difference to tell these two apart is to look for that carbonyl stretch, because that's going to be lacking in the octylamine here. Okay. When we look at nitriles have a really specific peak here at about 2250, and so that indicates to us that there's a nitrile there. And then finally, we are going to just summarize what we've seen. Here are the absorption peaks. I am not going to ask you to quote these absorption peaks to me, right? And we're going to do some Plicker questions where you can see kind of how questions would be asked. But you do need to know the ranges, because if I put a spectra on an exam, you need to be able to identify, hey, look, that's an alcohol, or there's a carbonyl that shows up at 1700. You need to be able to identify the functional groups in it. And the best way to do that is to know where they are. Now, I'm not going to ask what's the range for an alcohol, but I may say, oh, there's a broad peak at 3600. What functional group would that indicate? And then you would say, oh, yes, that would indicate an alcohol group. So again, we are going to practice this in class. And if you have any questions, please stop by my office.